Welcome back, everybody. Today we're going to continue with the B vitamins and move on to vitamin B3, which is niacin. So, niacin was actually discovered in the early 1900s. And again, it kind of, relates back to that whole disease state. And then they found that the disease was related to some type of nutrient, some type of food component nutrient deficiency. So, in the early 1900s, in the southern part of the United States, there were a lot of people that were basically displaying this disease that at the time they called black tongue disease. And the main manifestation of this was kind of these like almost patchy, scaly skin that kind of almost looked like burns, kind of almost like charred skin, actually. So many people were developing those, and then dogs were developing black tongues. So, all in all, they called it black tongue disease. And at the time, then, corn was a staple food. So, most people were kind of eating corn as one of their main kind of energy sources. And unfortunately, corn contains a biologically unavailable form of niacin. So it is possible to release a little bit of niacin from corn because corn does have a lot of niacin in it, but our bodies just can't get to it. And we'll go over that in a second. So you can release it with a little bit of alkali water, but again, I'll show you that in a second. But, in general, since we're eating so much corn, and since the corn had niacin in it, which we couldn't get to, basically that's why everyone was developing, these skin lesions. So that disease was later on called pellagra, and niacin was isolated. I'm not sure if it was from corn or what food source they finally isolated it from, but in the 1930s, they found that, niacin was basically the reason that people were developing that form of dermatitis. And they found that if someone was supplemented with niacin, it could actually cure the lesions, sorry. So it wasn't like a permanent thing. With a lot of the B vitamins, um, the symptoms do go away. I have heard that, how it's usually like dermatitis and like some type of neuro symptoms like paralysis, numbness, that type of thing. The paralysis, I think, gets a little bit better, but I don't think all of the neuro symptoms completely go away. Whereas, from my understanding, the dermatitis can pretty much be completely solved with the supplementation of whatever, or just like a complex of B vitamins. So, kind of same thing here, where those skin lesions actually just healed up once people were given the niacin. And yeah, it's called B3 because it was the third vitamin discovered. So now to go into some of the structural stuff with niacin, it's basically a generic term for two compounds. One is nicotinic acid, and the other one is nicotinamide. So if you read food labels and stuff, you'll often see nicotinamide, um, you know, listed as some type of supplement they might have put in, like cereal or something like that. The vitamin activity is provided by both of these compounds. However, to be honest with you, I mainly it once we get into the next slides where we look at the coenzyme form, you'll see that it pretty much has to be in this form to be a part of a coenzyme. So the textbook isn't explicitly clear, but from my understanding, nicotinic acid needs to be converted into nicotinamide before it can then go on to participate as a coenzyme. So I'll show you more of that on the next slide as well, just to clarify that. So nicotinic acid is a little bit different. You see, they're pretty similar, but this one's different in that it has this carboxyl group here. And then nicotinamide has an amide. So that's the functional group of that one. So basically, it's an acyl group linked to a nitrogen atom. So the coenzyme form of niacin is a little bit more complicated than some of the other ones. If you remember with thiamine, you're basically just adding a couple phosphate groups, so that was pretty simple. So this one, here we're dealing with nicotinamide, so we're going to start looking at the slide right here. And remember, nicotinamide is this guy. It's the same thing we were looking at right there. So this needs to be converted into this, nicotinamide. And then nicotinamide can then go on to become one of the coenzyme forms. So nicotinamide, in order to make it into one of the two coenzyme forms, which are NAD, which you probably recognize, and NADP. So NAD is nicotinamide adenine dinucleotide, and NADP is just nicotinamide adenine dinucleotide phosphate. So really with just a phosphate group attached. And I know I remember when I was taking this class, I was like, oh wow, I've seen this everywhere, in like intermediate metabolism. But who knew that every time you saw these guys, this is niacin. You need niacin every single time to make these because nicotinamide is kind of the base of that. So in order to make these two coenzyme forms, NAD and NADP, you take your nicotinamide, then you add a ribose group, and then on top of that, you have to add an adenosine. And then in order to kind of finalize it and make it into either NAD or NADP, if you're making it into NAD right here, you're adding a hydrogen atom. And if you're making this into NADP, or if the body is, you would just add a phosphate group here. So NAD and NADP, you could tell kind of by the names, are virtually identical. The only difference is that one is a hydrogen group here, and then the other one has the phosphate group here. Even though they do look similar, they have very, very different functional roles in the body, and obviously we'll go through all that in detail as well. But key things to remember from this slide, you start with nicotinamide. That's niacin in its basic form. Just like all the other B vitamins, it has to be in a coenzyme form in order to participate in its function in the body. And niacin has two coenzyme forms, NAD and NADP. So they look similar, but they're two totally different compounds in the body. Food sources, I'd say pretty similar to what we saw with the other ones. So meats and grains. The B vitamins, again, I'm always trying to show you like the patterns just because it's going to be really hard to remember these. I remember when I took this class, obviously like 20 years ago or something, but I had just finished taking my vitamins and minerals class, and I was in a pharmacy with a friend of mine, and she like picked up this lip balm and she said, oh wow, this one has B5 in it. Why would B5 be in a lip balm? And I couldn't remember anything about the B vitamins. I just felt so bombarded with information in this class that I was like, I don't remember what any of the B vitamins do, let alone like B5. So that's why I'm trying to show you there's patterns to these where like all the B vitamins for the most part have similar food sources. They have functional similarities. They have similarities in terms of deficiency, with dermatitis and neurosymptoms, that type of thing. So again, I'll keep on reiterating those over and over again, just so hopefully you remember some of this stuff like a year from now. So the RDAs for niacin, before we get into this, are 14 milligrams per day for women and 16 milligrams for men. So you can list those there and then kind of do some cross comparisons. So again, meats and grains, major food sources. A lot of kind of, like chicken, liver, if you eat that, has most of the niacin you're going to need for the day. So just in like one serving of meat, you're getting pretty much most of the niacin. In terms of more of the grain side, so you can like whatever breakfast cereals, that type of thing, most of those just supply 25 to about 33%, or about a third of what you need for niacin. So if you start looking at the sides like nutrition labels, you'll notice it's about a quarter to a third of what you need for niacin in most of those breakfast cereals and other kind of fortified grain products. And then, you can find it in beans and peanut butter and some other things like that in much smaller quantities. When we get niacin from animal sources, it is basically found in its coenzyme form. So remember, NAD, NADP, totally different things, and these are the coenzyme forms of niacin. So when you're eating meat, this is what you're ingesting into your body. So not the nicotinamide form, not the basic niacin form. You're basically ingesting it as the coenzyme niacin form. However, when we're getting niacin from a plant source, so from corn or something like that, you're actually getting it as niacin, which means that the niacin is attached to a carbohydrate. Or alternatively, the plant is providing it as niacinogen, and that's when the niacin is attached to a protein. So it's basically covalently bonded to these things. So that's a very, very strong bond between niacin with the protein or the carbohydrate. It's found in corn and wheat. So you can definitely, there is some in corn and wheat, but unfortunately our bodies can't really break this bond between the carbohydrate and the protein and niacin, so most of it is left kind of unavailable. So when we are getting niacin from plant sources, for the most part, we're getting it from kind of enriched or fortified products where the niacin has been added, since it's difficult to get niacin from plant sources. You can get a very small amount of niacin from corn if you treat it with lime water. So this isn't like lemons and limes. It's not like the citrus fruit. Lime water is basically from limestone. When you mix limestone with a little bit of water, it's what's the chemical? It's calcium hydroxide, I believe. And you're kind of mixing that, and you kind of like grind it up in Mexico and then in other kind of Latin cultures, they actually do this to prepare like tortillas and stuff like that. And it's really interesting because they've been doing that for hundreds and hundreds of years. And it's really cool to find, they just knew to do that somehow. And maybe, I'm not sure why, maybe it was like something that they found that could prevent that type of dermatitis with pellagra, since corn is a staple food source in those food cultures. So it's really interesting that they figured that out so early on. But even if you do treat the corn with lime water, so again, kind of like breaking it up with that processing, you're only liberating about 10% of the niacin still. So you're not getting like all the niacin out of the corn, but you're getting a little bit, so that's good, I guess. We can also make niacin in our body from tryptophan. So that's another kind of a smaller source, but we definitely are constantly kind of making a little bit of niacin as well. So we make it in the liver, and we use about 3% of our ingested tryptophan to make niacin. So in order, just to kind of show you how much tryptophan you need to make 1 milligram of niacin, so remember we need 14 to 16 milligrams per day, you need 60 milligrams of tryptophan. So, and you can get that from like complete proteins. A lot of like animal sources, stuff like that, have complete proteins. But I'll show you a bit more in detail when we get to the DRI section of kind of how much protein you need to get those niacin equivalents. So in order to make niacin from tryptophan, it's kind of a long, arduous process here. If you look, it's like this multi-step process. So here you start with tryptophan, goes through all these steps. You do not need to memorize these or have well, I guess it's open book, so you won't be memorizing them, but you don't need to know those in particular. But one thing I do want to point out is that in order to make niacin from tryptophan, you actually need to use some other B vitamins in that process. So at this step here, this requires riboflavin. And then at this step, you need B6 in its coenzyme form, PLP, which we'll be learning about soon. So yeah, this is kind of just to show the interdependence of the B vitamins, that they're kind of used in each other's like metabolism and synthesis and stuff like that. In terms of cooking and niacin, this one's kind of special. It's very heat resistant. So you can do those things that we were talking about before that usually destroy B vitamins and the water-soluble vitamins, like pressure cooking, grilling, like barbecuing, that type of thing, deep frying, and you will not destroy the niacin. So if you are like barbecuing meats and stuff like that, you're not going to destroy the niacin in those because it is heat resistant up until about 250 Celsius. So that's quite high. In terms of boiling, because it is water soluble, it does follow the same pattern as everything else. So if you're, boiling whatever beans or vegetables, that type of thing, you can have some of that niacin seep out. So you do need to recoup that water in order to, get the niacin. But again, unfortunately, for most plant sources, that niacin is still going to be attached to those carbs or those proteins. So you really need to like chemically treat the plant sources to kind of liberate that. So again, it's kind of biologically unavailable unless the plant source has been enriched or fortified with niacin. Moving on to digestion. One pattern that I kind of want you to pick up on at this point, and maybe you have, is that you basically need to break down the vitamin into its most basic form to absorb it. So remember I was saying, first let's look at the digestion and absorption of niacin from animal sources. So remember we're getting that in the NAD and NADP form. So that's the coenzyme forms. That's kind of, that's kind of like what's stored, the form that's also stored in tissue. So if you're eating obviously like an animal muscle, that's the form that's stored in there. And remember, NAD, NADP, the coenzyme forms are made up of three components: niacin itself, so nicotinamide, ribose, and an adenosine. So in order to break it down, you actually use the enzyme glycohydrolase to kind of like just cut these two parts off. And then that way you're left with free nicotinamide. Now looking at kind of the digestion of plant sources of niacin. So remember that's the niacin where a carb is attached to niacin, or niacinogen where a protein is attached to niacin. If those aren't chemically treated with like lime water or whatever before, you're just going to excrete that, unfortunately. So there's no way for your body to kind of break that very tight covalent bond. So that's basically not going to enter the body. Absorption of niacin follows very similar pattern to everything else. So try to remind yourself, what's that pattern? What happens at high intakes of niacin or of any water-soluble vitamin? At high intakes, does the body want to use energy? No. So at high intakes, the body's like, okay, we're getting enough of this. I'm not going to spend any time or energy on bringing this into the body. And then at low intakes, will the body expend energy or resources? Yes. At low intakes, the body will use some type of like sodium dependent or independent transporter, some type of like energy dependent or resource dependent process to bring it in, usually through some type of carrier. So very similar to what we saw with basically all the other B vitamins so far. In the blood, niacin's transported attached to immunoglobulins, albumin, and fibrogen. And at this stage, remember, we're dealing with nicotinamide. So that's the most basic form of niacin. So not the NAD or NADP form. We kind of broke that down and simplified niacin back into its basic form in order to absorb it and then also to transport it around the body. In terms of how it's absorbed into tissues, it's kind of dependent on tissue type. So in order for nicotinamide to get into red blood cells or the kidney, it does need to use a niacin carrier. So it's a carrier-mediated process for red cells and the kidney. Whereas for all other tissues of the body, and it's pretty much found all over the body, again, because B vitamins basically help the Krebs cycle and glycolysis just work. So obviously that's found in pretty much every single tissue, every single cell of the body. So they're found pretty much everywhere. So when it's getting into all those other tissues, it's just passive diffusion to get in there. In terms of what happens once it's in the tissue or once it kind of enters the cell, nicotinamide is pretty much immediately converted into its coenzyme forms. So remember, what are the two? NAD and NADP are the two active coenzyme forms. So once they're converted, unfortunately, NAD and NADP are kind of trapped within that cell. And if you want to actually get them out of the cell, you kind of have to break them down again into the most simple form of niacin, nicotinamide, in order to get out. So kind of similar to what we saw with absorption. And you'll notice that with a lot, like even when we get to the mineral section, these things are kind of built back up within the tissues and the cells, but in order to cross back out or to kind of travel around the blood, the body will actually kind of break it down to its most basic form. So, and then also just to point out, most cells have higher amounts of NAD than NADP, and that's just in relation to their actual functions, which we'll talk about momentarily. NAD, another thing to remember once it's in the cell, NAD is found predominantly in its oxidized form, so it's already given away its electrons, whereas NADP is found in its reduced form, so it still has those electrons. And then just to kind of go over kind of a brief summary of this, when in transport, niacin as nicotinamide, so remember nicotinamide is that most basic form of niacin, it's also just another word for niacin, is generally in its free form. Again, when crossing membranes, it needs to be in its kind of smallest, most basic form, so the free form as nicotinamide. And then the second it kind of enters tissues and cells, the body wants to start using it, and obviously it cannot use it until it's in its active coenzyme form. The active coenzyme form is NAD and NADP, so it's kind of instantly converted to those two things. So the body can use it, basically. So now to go through the different functions and try to remember what the differences are. Again, they look so similar, NAD and NADP, but they do totally different roles in the body. So if you remember NAD, that's the one that you saw in glycolysis and in the Krebs cycle. That's the one that helps with ATP generation, kind of going on to the electron transport chain. Whereas NADP or NADPH, that's the one that has the role in all this kind of like synthesis and building things. So when you're kind of synthesizing fatty acids and cholesterol or DNA, it's also involved in the regeneration of glutathione. So this one is not the one that you see in the Krebs cycle. You're only seeing this one, just to kind of clarify that. In general, both of them have like an overall similar function, but they're used in different parts of the body. So the main thing they do is they act as hydrogen donors and electron acceptors. So they can both like give and accept electrons. So they're kind of just like passing electrons around the body for the most part. So they're involved in these oxidative kind of reductive processes. And as I mentioned several times before, even though they look similar, they have very different functions. So first, NAD, that's the one that collects electrons from intermediate metabolism. It transfers these electrons to the electron transport chain, which then generates ATP. So NAD is the ATP generating one. NADPH, that's all these kind of reduction reactions that are basically synthesizing things. So fatty acids, cholesterol, DNA, and it's also involved in the regeneration of glutathione. So where did we see glutathione before? What does that do in the body or in relation to vitamins? So that's the one that regenerates vitamin C. So that's the one that kind of gives its electrons to vitamin C. So vitamin C can then continue to kind of keep on donating electrons to other things. So NADPH, niacin, it's kind of this whole electron passing thing, as I was saying before. NADPH gives electrons to glutathione. Glutathione then hands them over to vitamin C, and then vitamin C gives them to a whole bunch of other things. So the body can keep on chugging along, basically. So, specifically, just to remind you where you've seen NAD before. So, this is that kind of ATP generating one. That one is in the step between glyceraldehyde 3 phosphate to 1,2 diphosphoglycerate. So, in glycolysis, if you remember, you're generating two of those there. You've also seen it in the oxidative decarboxylation of pyruvate, so in that step. And then also in the oxidation of acetyl-CoA in the Krebs cycle. So you're generating three of those throughout the Krebs cycle. In terms of NADPH, that one is actually made by the hexomonophosphate shunt. Feel free to cross that out and put the PPP if that is what you're more familiar with. Again, they're both the same thing. So we did talk about this in a previous lecture. What vitamin helps to make NADPH? When we discussed the function of a previous vitamin, what was it? Thiamine. So the answer is thiamine. I'm never sure how much time to give you guys as I'm recording this because I usually just wait for people to actually answer it in class. But, you can pause it or whatever if you really want to give yourself a memory jog or something. So, again, NADPH, as we discussed several times already, that's the one that helps make things, so fatty acids, cholesterol, DNA, and it also helps in the regeneration of glutathione. So this one, again, not involved in Krebs cycle, electron transport chain, anything like that, just in making things. And it is made by that extra process that kind of like shunts off of glycolysis, so the hexomonophosphate shunt or the pentose phosphate pathway. When you're excreting niacin, the first thing your body does is obviously, to get it out of something, it needs to break it down from a cell or a tissue, needs to break it down into its most basic form. So remember, that's nicotinamide. The enzyme that does that is glycohydrolase. And it's also found in the small intestine. But basically, if you're going to excrete nicotinamide, that's the first step. You break it down to that. And then eventually it's also broken down into other kind of smaller metabolites. And that's important because the body actually won't excrete it, or the kidney won't excrete nicotinamide itself. It needs to be in the metabolite form. It's kind of a cue to the kidney that if it's processing or filtering nicotinamide, so it will reabsorb it if it's still in that vitamin form. But if it's kind of been made by the liver into these metabolites, then it kind of clues in the kidney that, okay, now it can be excreted. But if it's not in its metabolite form, it will be reabsorbed by the kidney. So that's generally, kind of a feedback mechanism there for excretion. As I mentioned before, there is an RDA set for niacin. It's 14 for women, 16 for men, and it's milligrams per day. And the rationale is very similar to what we've seen before. So it's from those balance studies where they kind of relate dietary intake to excretion and also signs of deficiency. So those signs of pellagra that we saw before. And it's also based on urinary excretion of metabolites. So they're kind of just measuring what goes in, what goes out, and making sure that people aren't getting any signs of deficiency. So now to go into a bit more detail about niacin equivalents, which I'm not sure, maybe you've heard of these before. So nutrition labels, if you look at any nutrition label on the side of a box or whatever it is, that only accounts for preformed available niacin. So if you have whatever plant product, they're not going to list the amount of niacin that's in there that your body doesn't have access to. So all the ones that are attached to carbs and proteins, those won't be listed. But anything that your body does have access to, it will list that. So, usually that's like with any grains, it's usually like a fortified or enriched product. So then they'll say kind of like how much extra niacin has been added and how much your body can kind of get from that food. So that's kind of like the preformed or available niacin. So anything listed on there is what your body can actually get. Kind of ignores all the stuff that's like attached to carbs and proteins that you can't get. And then there's something else called niacin equivalents, which I don't think you're going to actually see on, they basically don't list this, but this is something that you can kind of calculate yourself to see how much niacin you're getting from protein. Because remember, you can make niacin from tryptophan, and obviously tryptophan comes from protein. So one niacin equivalent is just kind of a fancy way of saying 1 milligram of niacin. And remember from our previous slides that 60 milligrams of niacin, of tryptophan, are needed to make that 1 milligram of niacin. So to kind of show you a little bit more, so how do you get that, or how much protein do you need to get that much tryptophan? So 1 gram of complete protein will give you 10 milligrams of tryptophan. And then remember, here's that other conversion, 1 niacin equivalent, which is 1 milligram of niacin, is equivalent to 60 milligrams of tryptophan. So you kind of see where I'm going here. In order to kind of figure all this out, obviously, now that you have these conversions, you can do it any way you want. But if you need a little help of how to kind of set up these equations, this is the way I usually do it. First, I calculate how much tryptophan I can get from that complete protein and, set it up any way that you want. But basically, 1 gram of protein, remember, is 10 milligrams of tryptophan. So 60 grams of protein then would be, how many, and then you can just kind of cross multiply to figure that one out. If I do ask you this question on an exam, please remember to list these conversions. So both of them. Just because, if you make a mistake somewhere, I'll know kind of, oh, maybe you messed up what the conversions were to begin with, but you kind of understand the process. So you might be able to get extra points in that way. And then the next step is just to calculate the amount of niacin or niacin equivalents from that tryptophan. So again, you kind of set it up using those conversions and then cross multiply. So the answer is 60 milligrams of niacin or niacin equivalents. And if you want, you can kind of practice that on your own with some other numbers, but I kind of left you a bit of space here on this slide if you want to calculate how much you can get with 78 grams of protein. So the deficiency disease for niacin is pellagra, which I mentioned before. It's still quite common in places like rural South America. It's also seen in Africa, Mexico, and Indonesia. And it's pretty common, particularly where corn is a staple food. And again, that's because it basically provides a type of niacin that's kind of stuck very, very concretely onto like a protein or a carb, so we can't have it, or our bodies don't have access to it unless you treat it with like a little bit of lime water, but still then you're not getting a lot of that niacin. The deficiency symptoms of pellagra are also called the 4Ds. So really quickly as I go into this, I just want you to kind of relate it back to some of the other things we've seen with the other B vitamins. So one of the Ds is dermatitis. And then it's a really particular type of dermatitis. It looks a little bit different from the other B vitamins. It kind of covers the whole body. If you remember riboflavin, it was more like around the mouth. But in this case, it's really particularly kind of around the neck, and it's also on the extremities. So it's on the arms and legs. And it does look kind of like a sunburn. It's kind of this like chalky looking burn look of type of dermatitis. Dementia can also occur, so like memory loss, paralysis, numbness. Diarrhea is another thing that can happen, so there also are some GI symptoms to it. And then obviously death if left untreated. So the 4Ds are dermatitis, dementia, diarrhea, and death. And then if you kind of link it back to everything else we learned, it's just the main two things that you're really seeing with the B vitamin deficiencies are dermatitis and neuro kind of issues like numbness and paralysis. So it kind of, it's similar to that. But that also makes it really hard with B vitamin deficiencies to kind of pinpoint exactly what B vitamin you're deficient in. I think with niacin, the dermatitis is more of a particular pattern, so you can kind of tease that out from the other ones. But at the same time, it's always best to just supplement with a B complex just in case. And that tends to get rid of the dermatitis. But sometimes, if the paralysis or the numbness is pretty far gone, it's hard to get all that, the nervous system to kind of start working totally perfectly again. So, who is at risk for this? Very similar people to who we discussed before. So, anyone with malabsorption disorders like Crohn's disease, ulcerative colitis, even just irritable bowel syndrome. Obviously, people that are kind of processing foods really quickly, or where food is just kind of being shunted throughout the GI system really quickly. The body is not going to have time to absorb it as well. Or maybe, parts of the intestinal tract are just malfunctioning or just like eroded or anything like that. So you wouldn't be able to absorb it as well, obviously. Alcoholics and the elderly, so both of them have decreased food intake and absorption problems. Those are the main reasons that they tend to be people that suffer from B vitamin deficiencies, or they can be. And then also people taking tuberculosis medications. A lot of these medications will bind B6, and if you remember from a previous slide in this lecture, that B6 is required to make niacin from tryptophan. So it can, people on TB medications, it's been shown that some of them will develop pellagra. The TUL for niacin is probably one of the most interesting parts. It's the main thing that I remember, honestly, about this. First thing I want to show you is that, look, the TUL is actually like pretty low. If you remember with a lot of the other water-soluble vitamins, they were pretty different. Like they were in the hundreds, whereas here it's only about twice the amount of what we see for the RDA. And there are some pretty extreme acute effects that you're going to get from consuming even slightly higher amounts of niacin. So some people even get this when they're just consuming the amount that's found in like a Centrum or, whatever kind of like multi-vitamin mineral thing you're taking. So the main effects that people see are vasodilation. They have, it's accompanied by it's from increased histamine release, and then you get this kind of like red skin, flushing and itching. People look, I'll show you in a second, but it looks pretty intense. The other thing that some people get is nausea, vomiting, heartburn, that type of thing. And then chronically, it's been shown that some people will get gout. So niacin competes for uric acid, for excretion in the kidney, competes with it, and then also liver injury can occur as well. So this is what I was talking about as like an acute reaction. It's called the niacin flush. So this happens within about half an hour or so of taking pretty high doses of niacin. You kind of get like super red, very itchy. Apparently it's not very comfortable. I always ask at this point when I'm teaching this in person if anyone's done this, and there's usually one or two people in the class that have done it. I personally haven't done it. I'm a little scared to do it. It seems a little uncomfortable, but I always say like, oh, I should probably do it just so I have like some type of story to say like in this class, because it does seem kind of interesting. So then you're probably wondering, well, why would people do this to themselves? In general, niacin is super interesting because it's used to kind of combat hypercholesterolemia. It's basically one of the only kind of medications or supplements that can actually help correct all four forms of dyslipidemia. So if you have high total cholesterol, high levels of LDL, high triglycerides, and low HDL, niacin has been shown in several clinical studies to correct all four. And that's really interesting because right now, they're not quite sure how it corrects low HDL, but right now the only two things that can actually raise good cholesterol, HDL, is exercise. So you need to do that at least 5 times a week for the course of months to start to see your HDL go up with exercise. But niacin is the only kind of like pharmaceutical way to actually increase it. So when you're taking statins and stuff like that, those drugs are just targeted towards LDL. and they don't raise HDL. So basically, all the pharmaceutical companies are really trying to figure out what does niacin do to help raise HDL? Because, once they figure that pathway out, they can then, I'm sure, turn it into a pill and sell it for billions of dollars or whatever. But so yeah, niacin's really interesting in that it can fight kind of like dyslipidemia, high cholesterol levels. Unfortunately, you need really high amounts of niacin for that. So you need 6 grams per day, divided over the day. So a lot of times you'll get, and again, once you start, if you do start looking at like Target and Walgreens, you'll see that there's a ton of niacin. This is the main thing that niacin is marketed for, kind of cholesterol therapy, basically. And a lot of them are now like slow release, so you get less of that whole like flushing reaction. But from what I've seen, you take 3 doses a day, 2 grams per day. So that's 2,000 milligrams. So it's a lot compared to the 14 or 16 that you should be taking. So you're kind of like really hyperdosing your body with it. And then it's usually provided as nicotinamide if you're interested in exactly what they're giving you. So some of the possible mechanisms of action of how it's helping cholesterol levels, it has been shown, so niacin has been shown to inhibit hepatic VLDL synthesis. So remember from Dr. Song's class, that's kind of the precursor to LDL. So then that eventually helps to lower LDL in the circulation. Niacin also inhibits diacylglycerol acyltransferase and thereby decreases triglyceride synthesis. So that's another thing it does kind of in the liver, and that helps lower TGs. The mechanism by which it increases HDL is still not fully understood. So again, basically exercise and niacin are the only two things that we know of that can help increase HDL. Which is still really interesting. I'm surprised they haven't come up with some type of pharmaceutical therapy to help raise that, because it is really important for heart health to have higher HDL. And that's it actually. So we do have our live Q&A section. So any questions you have about supplementing with that, I can't really think of any of the other questions right now that people usually ask. But people often ask like, oh, well, how does it feel? And it's interesting in kind of the live class to talk to people that have actually done it and see how they felt doing it. Some people don't mind it. Well, I've definitely had people in the class before that kind of like take it really regularly for cholesterol, or I think it's probably marketed for other things too. But in terms of actual clinical trial data, the only thing that I've seen that's actually been proven is decreasing cholesterol levels. And so if you do want to kind of tell clients to use it, I'd say, definitely it's something that has been shown. So if they're scared of using statins, can result in like impaired wound healing and some liver injury and stuff. So some people are really scared of taking statins. Definitely work with their doctors, and maybe niacin would be a good thing for them, but you really do have to warn them about the niacin flushing, because I think for a lot of people it's not very fun. Again, it happens within about half an hour, and then I think it lasts for half an hour to an hour. So it's, if you're taking like 3 of these doses a day, you have at least 3 of your hours a day where you're just feeling like itchy and uncomfortable. So definitely something to take into consideration. All right, so just to do a quick review here, what are the 2 major things that B vitamins do? What's the main one that we've talked about over and over again? Energy metabolism, so Krebs cycle, etc. And then what's the one that we haven't talked about yet? Blood cell formation, hematopoiesis, exactly. Great. Okay, so really quickly, let's just go through kind of what these things do. So let's just stick to the B vitamins for this one. What are the food sources, a general food source for all of these? Meats and grains, yep. So just remember, if you're at a party or something and someone puts you on the spot, they're like, how do I get riboflavin? Hopefully it will come to your mind like, oh, meats and grains, just because that happens to me all the time. So it's nice to have these like patterns to kind of memorize or just know. Functions, we can do this in a little bit of detail. So what was thiamine doing? Do you remember? So if you remember, that was with the decarboxylation of pyruvate, alpha ketoglutarate to succinyl-CoA. and then also synthesis of NADPH, which we talked about today, and nerve conduction as well. What is the deficiency disease of thiamine? It's beriberi. And then what's the one that you see in alcoholics with the eye, Wernicke's encephalopathy? Yep. Is there toxicity for this? No, no toxicity. It's just not established. So function of riboflavin, what you can kind of even think back to its coenzyme form. Maybe that will help you remember. Remember those coenzymes are called flavoproteins, and basically they help in their oxidizing agents. They help also mainly, remember it's like FAD, so I remember seeing that when I was taking this class in the electron transport chain, so that kind of helped me remember what it does. So kind of an ATP generation there. The deficiency of that, remember it's like dermatitis around the mouth related stuff, and that was called a riboflavinosis. What's the toxicity of riboflavin? It's nothing. Basically, it's not established yet. You can take really high amounts and be fine. Niacin function. So remember, there's two coenzymes, and they do totally different things. First one is NAD. What does NAD do? It's involved in ATP production, and then NADPH. What does that one do? That one helps build things, so cholesterol, fats, that type of thing. Deficiency is called pellagra. And then probably the most interesting thing about niacin is its toxicity effects. So that's the niacin flush. And remember, why would people take really high amounts of niacin, and why would people do this to themselves? Mainly to treat high cholesterol levels, and it does work. It's been shown again in dozens and dozens of clinical trials. So it's approved by the FDA and all of that. So anyway, yeah, that's one of the, I'd say probably the main thing you're going to remember about niacin, honestly, when you're done this class is the niacin flushing and the cholesterol treatment. Okay, great. Well, yeah, I'm happy to answer any questions during our live Q&A session, and have a great rest of your day.